Okay, so today our speaker is Vladislav Pokidkin, and he will tell us about compact quantum metric spaces and convergence for quantum Gromov Hausdorff distance. Please.
Good afternoon, and let's start. The plan of my talk will be the following. First, we give a definition and motivation for compact quantum metric spaces. When we provide some sources example and try to show Dirac a great approach for building compact quantum metric spaces. When we introduce Gromov Hausdorff distance for such spaces, and then we will talk about recent results concerning convergence of such spaces for this Gromov Hausdorff distance. Initially, inspiration was found in high energy physics and in string theory, and they had such cases, and this theory started with Kaad's spectral triple. If we consider Hilbert space, star algebra representing bounded operators on this space, and if we introduce a self-invariant operator on this space, we can get some data, and this triple, these three elements, if we will name this spectral triple. Kaad have noticed that for every spectral triple, we can obtain metric on this space of states by the following construction. We take supremum between difference values of states on that element of algebra, and we consider such elements of our star algebra that their norm commutator norm of commutator is less than 1. I will say what is mean state space a little bit later, and it was one of the first works from which theory starts. So then Rieffel have noticed that if we have a compact metric space, we have some relations between algebra of continuous function for that space and seminorm on that space, and we build seminorm on the space of on algebra of continuous functions by such a way, and also we can recover metric from seminorm, and he wrote in his previous articles that it's natural to suppose that it's natural desire to suppose that topologies of the weak topology on the space of states, and the weak and topology generated by generated by metric should coincide. And yes, Kantorovich in his articles has showed two important results that on the we can define metric on the space of states by the following way through semi-norm. And also he has shown that these topologies coincide. So we have the following. I think that the data set of continuous function on our space and semi-norm on that space somehow equivalent to the data the data of metric space. So we can reformulate. So we have such results for commutative states when system algebra commutative, and it hints us what should we do for non-commutative case. So we should pay attention on the space of continuous functions, on the space of functions and semi-norm, and do something similar. And in Kahn's example, this norm of commutator it provides actually semi-norm on the space state. So it was some preliminary discussion, and in our work we will consider order unit space. For our purposes, it's better to understand that it can be realized like a norm space with a partial order, and it is somehow like a vector space of self-adjoint operators, and it should contain unit operator. The strict definition for us not too much important, but I will read it. According to Carrison, order unit space is particular order vector space with distinguished element, and it should satisfy two properties: order unit property and Archimedean property, which you can see on the slide. And for such spaces, there is a natural norm defined by the following way. For any order unit space, so with this norm, order unit space is norm space, and we can consider its dual space and dual norm, dual space of bounded linear functionals. And we can define a state as such element, such bounded linear functional that it has values on unit element like unit, and it coincides with norm on that dual space. And state space we will name like a collection of all states. And it shows that this space is bounded, closed, convex subspace of our dual space, and it's also compact for weak topology on that dual space. Okay, we can now we have some. Now we somehow understand how can look state space, and if we return something more close to ICO, we can provide the norm, semi-norm on our space of states. We can provide metric by using semi-norm in that space. And it's natural to demand the conditions that values of semi-norm on unit should equals 0. It is connected with definition, or is connected with the case for just ordinary metric space, and we want to see something similar like convergence results for commutative case to demand the equality of the following topologies. So all that leads us to definition compact quantum metric space. Let A be order unit space, S of A is state space, and first we define lip norm. Lip norm on order unit is just semi-norm with the same properties which we showed on the previous slide. And compact quantum metric space is pair of order unit space and the Lipschitz norm on that space. So it's formal definition. And as we understand, Quant's example provides compact. Quant's example, which we considered above, is just a simple example of compact quantum metric space, but it is for commutative case, but the notion is more general. So we have received some definition, but as you can understand, that checking that equalities, checking that topologies coincide is rather difficult, and it's not clear how to deal with it. And first we discussed some examples. In some article, it was shown that every separable order unit space has an abundance of Lipschitz norms, and yes, definitely, it's not clear how to construct these Lip norms. But for separable case, there is some unnatural construction, but that you can find a lot of them, and there are some specific articles. But most interesting constructions of this norm come from action of groups. And in some sense, we can say that all Lip norms come from action of Lip groups. It's unstrict. And now we try to show it. If we consider unit of C star algebra and locally compact group with strongly action on that algebra, we can define seminorm by using length function. On the slide, you can see the definition of length function, and the simplest example of length function can be if we consider if our group will be just real functions, and this function L is just module, taking module. Our group is real numbers with with some structure. So x inverse, it will be just -6 in that case. And module is an example of length function, simple. Then we can define, for that case, we can define a seminorm as follows. So a supremum of difference between action of our group on element.
I'm sorry, what is an IXY? Is it multiplication or?
XY.
In your definition of length function, x comma y should probably be x multiplied by y. Is that correct? In your definition of a length function. That means the product of x and y.
Yeah. Yes. It should be.
Oh, just multiplication.
Yes. Thanks. Thanks for comment, and also be free to ask, and if you have something add or correct, always be free to do that. So we define a seminorm on our unit of C-star algebra with help with length function, and it shows that the set of such elements from our star algebra, such that their value of seminorm on that element is less than infinity, is dense star subalgebra of A for some length function. So and it will be useful for us a little bit later, and we know some useful example, some useful construction for building compact quantum metric spaces via introducing ergodic action. And ergodic action is such action that invariant elements of this action are just elements from complex plane. And we have theorem that for compact group and ergodic action, the seminorm which we have showed on the previous, which we have built on the previous slide, is a Lipschitz norm. And this easily fails if J is not compact. And also in non-commutative case, we should demand more far action. In some article, in one article, non-commutative, non-compact case, one of was studied only was studied for Heisenberg-Lie groups on non-commutative Heisenberg manifolds, but it is another topic, and usually we will consider compact groups, and for compact groups, everything is fine. So let's consider some example, and we said that definitely group up for purposes it's useful to consider reaction of different reaction of a group, and if we consider Lie group with some function, some action, we can define a function from our group to complex numbers that its values is just values of it just coincides with action of the group. We can form some subalgebra. I remind you that here I is A is C star algebra. And we can form some subalgebra, such elements that the built above function is infinitely continuous. Then for that case, it's true that it proves that infinity is dense subalgebra, and the action of the group gives us presentation of the algebra by derivations. And if, for example, if we if we choose some element of our group, Lie group, and fix it, it's somehow clear that we get an operator from A infinity to infinity function, and it is somehow clear that it's really a representation of the algebra. Differential operator we will define by fixing element of A infinity, and it defines it defines for taking value of this action for any element of Lie algebra G. On our Lie algebra G, we can choose norm, and then it's also some statement that then this differential operator, its norm, we can use it as semi-norm for our A infinity subalgebra. And if our Lie group is compact, when by theorem above, we get that L is a Lipschitz norm, and our pair A infinity and L is a compact quantum metric space. We only actually I don't understand. So I think we should pay attention that A infinity is dense star subalgebra, and probably I don't know. Can we consider completion of A infinity and A, but this pair should be compact quantum metric space according to definition. So we understand that if we have compact group and ergodic action, when we can build Lipschitz norm, when we can ask how to build ergodic actions. And actually there are three well-known constructions for building beta actions. I will discuss only one because it's the simplest example, but there are another two constructions for compact abelian groups, for closed subgroups, and the construction of ergodic function is well known for compact group, and for that group we consider reducible representation on Hilbert's base and consider algebra of bounded linear operators on our Hilbert space, and ergodic. It shows that ergodic action can be ergodic action builds by using irreducible representation. Alpha x t equals such joint action. For abelian groups, there is some article. There is one article. It shows that the second for abelian groups, the second and the third construction gives all ergodic actions. But for non-abelian compact groups, there is no known classification of possible ergodic actions. But it was article of my presentation founds on the Rieffel article, which was written at the beginning of this millennium. Probably it's not the case. And in this article also is written that it's unknown whether SU4 special entry group dimension 4 has any ergodic actions other than obtained from these constructions. Another instrument for building compact quantum metric spaces is by considering some subspace of order unit space, and it shows that restriction of Lipschitz norm of order unit space is also Lipschitz norm. the simplest example of that construction can be shown for non-commutative theory, and for non-commutative theory, we can build some subspace which is compact quantum metric space. Let's turn to Dirac approach for building quantum compact spaces. And his idea one of ideas is similar to the previous statement that we consider some algebra and try to find some star subalgebra, which is compact quantum metric space, but we use some special properties of continuous length function. And for the Dirac operators, we had that we can formulate for Con's example, we can formulate approach by following. Our Lie group is just R. Our strongly continuous representation of R is U. There is infinitesimal generator of our representation, and by calculus, our representation should be exponent of E80 t in the power of generator. Algebra functions. Our algebra, we also consider action of our real group on star algebra and define action by the following way. It's similar to the first construction, which I have shown previously. And for that construction, it's true that if for every element of our star algebra B of bounded linear operators, we can define some function which maps from our group to this algebra, and its values is just action. And for that, if this function ft is twice differentiable, then commutator with differential and this element from our star algebra should be in the subset B of t. B of t, it is subset star subalgebra of B such that somehow its action is strongly continuous. It reminds us previous slide that we consider some algebra when we can find some subalgebra with length some subalgebra in our case B beta, such that B beta L is compact quantum metric space. But we should the length function in that case is as the previous example example of module. Also, it's true that if our function ft is twice differentiable, then the norm of commutator is just supremum. And here we can see that module t is definitely the length function, and the construction in this lemma is similar to what we have started at the beginning. Like here. There is for our subalgebra A, A is star subalgebra B beta such that our these operators are bounded, and for this subalgebra, the following sim norms coincide. In general case, topologies are not equal on the space of states for that case, but there are examples when it is the case. The Dirac approach for can consist in that we consider our space, and we introduce some operator, and we build a semi-norm on algebra functions by means of norm of commutator or of self-adjoint operator with our element. We should in Dirac approach we considered triple, and we want to have such triple for compact metric spaces. We want to introduce that approach for compact metric spaces and compact quantum metric spaces. For compact metric spaces, our triple can be is just the set of function. Our Hilbert space will be L2Z omega. Omega is a restriction of square measure on our set Z. we consider differently this set Z, the square without diagonal, because in Kantorovich example, when we in Kantorovich example, we demand that X and Y shouldn't coincide. So that's why we consider that. So that's why we consider square of compact quantum metric space without diagonal. So we have again triple in that case will be algebra of continuous function with such norm. We introduce operator, the following operator, and for such operator, it shows that it's bounded if f is Lipschitz, and in that case, we also have that the norm of this, the norm of commutator, this operator D and our function is Lipschitz constant, and it also serves as for building semi-norm on the space the space of A. And something similar we can build for compact metric spaces. We also consider we consider compact metric space we've introduced above metric rho L. The space of states is compact metric space, and we consider its representation. We consider self-adjoint operator, and we use this self-adjoint operator to build semi-norm. And in that case, we should consider an inclusion of our I remind you that A according to definition is order unit space, and L is Lipschitz Lip norm because it's compact quantum metric space. So we considered inclusion from our order unit space to the space of representations on a Hilbert space. We provide this inclusion by following. And under this inclusion, the result is Lipschitz function, and its value is also Lipschitz constant. And it is a Dirac approach for compact quantum metric space. Probably it's not clear construction, but let's move forward. Let's discuss Gromov Hausdorff distance for such for quantum compact metric spaces. First, we define for every compact metric space R neighborhood of some subspace as the set of all points that distance between points of our subset between points lying in our subset and another point in our compact metric space is less than R. So we define the neighborhood by the following, and if we consider two closed subsets, we can define Hausdorff distance between these closed subsets as the infimum of such constants R that one space lies in the neighborhood of other, and another lies in neighborhood of other. And this distance, it's positive, and it's actually can be considered as a metric, on the space of closed sets of our space set. So we consider a compact metric space. We consider the set of all closed subsets of our space, and on that space, Hausdorff distance is metric for such spaces. Okay, now let's consider two different compact metric spaces. Let's consider disjoint union of such metric spaces and consider the set of all metrics on this disjoint union, such that restriction from disjoint union to one space provides us the metric on one space, and restriction on another space provides metric on another space. Then Gromov Hausdorff distance between compact metric spaces defines by infimum of all distances between space compact metric spaces X and Y according to metric on their disjoint union. So here we consider our total space is just disjoint union X and Y, and we have closed subspace X, closed subspace Y, and therefore we can consider Hausdorff distance between these metric spaces X and Y. And we can, by following a way, we define Gromov Hausdorff distance between metric spaces. It's just Gromov Hausdorff distance. Let's define. What's interesting that Gromov Hausdorff distance, Rieffel has shown in one of his works that if Gromov Hausdorff distance between quantum metric spaces is 0, then there is isometry between these two compact metric spaces, and therefore, in some sense, we can consider we can build the following metric space. Our space will be isometric classes of compact metric spaces, and our metric on that space will be Gromov Hausdorff distance. It's clear that Gromov Hausdorff distance is positive, and it shows that this distance serves as metric on that space, and according to the proposition, we have the following conclusion. Now let's try to define quantum Gromov Hausdorff distance. If we consider two compact quantum spaces, let's consider their sum, which is also will be order unit space. We have two projections from this sum. Then let's consider the set of all leap norms on that space with quotient seminorm. It means that we will consider such leap norms on our sum that they should provide us leap norm on their components A and B. So we have the sum of compact quantum metric spaces, some leap norm on this sum. We demand that our restriction from sum to one component should provide us our space, and restriction of seminorm on the sum should provide seminorm on the component. And similar stuff should be for the space of states of sum, and metric on the space of states. Our restriction from sum to component should give us the space of states with defined metric on that space, and restriction metric on the state of space of sum on one component should give us metric on that component. Quantum Gromov Hausdorff distance between quantum metric spaces we define as the infimum distance between our space of states. To understand this definition, we should remember that space of states SA and metric rho LA is metric space, and actually compact metric space. So it is we reduce this definition to the definition of Gromov Hausdorff distance between compact metric spaces, and here distance between that spaces defines the following, and we consider seminorm on the space of all seminorms LA and LB. Rieffel in his work also has shown that if quantum Gromov Hausdorff distance between compact quantum metric spaces is 0, then there is isometry between that spaces. And he also has shown an interesting theorem that the space of isometric classes of compact quantum metric spaces with quantum Gromov Hausdorff distance is actually complete metric space. It is one of his results. So for compact quantum Hausdorff spaces, we can define distance, and when we will consider convergence, we will build some spaces and discuss some recent results concerning convergence according to that Gromov Hausdorff distance. But at first we should remind some definitions to understand which spaces converges. We should provide some definitions, and universal unitary star algebra. It generates. It has generators A and B with following relations. Also, we can define coordinate algebra is the unit of subalgebra generated by two elements from universal unitary system algebra. As I understand the difference that A and B in the definition below cannot provide us the whole universal unitary system algebra. And coordinate algebra and those with structure of algebra. To define Podol's spheres, we consider strongly continuous circle action on coordinate algebra, quantum spatial unitary group, determined by generators, and this action is just multiplication. When we define such subspaces of our coordinate algebra, that strong continuous action is the following like z in the power n multiple x, and if n equals 0, we will name it coordinate algebra of quantum sphere. And standard Podol's sphere is C star completion of this A0 subset of coordinate algebra of quantum spatial unitary group, and its completion according to the norm inherited from from the whole space. This coordinate algebra of quantum sphere is generated by following elements, and it shows that the following set constitutes a vector space basis for a coordinate algebra or coordinate algebra. This space in this space we can see it's infinite dimensional space, but we can consider some subspace and some specific subspace names quantum phase sphere. The difference that it's also infinite. It is finite dimensional in that case, and it's easy to check that the dimension of this subspace n+1 square, and it shows that we can build some specific seminar on that quantum phase spheres, such that the obtained spheres will be compact quantum metric spaces. And now we can somehow understand the formulation of theorem which has proved in this year that if we consider these quantized phase spheres defined on the previous slide, these spheres they converge to photosphere with respect to compact with respect to quantum Gromov Hausdorff distance, and the similar result is that if we consider photosphere, they converges to classical sphere in quantum Gromov Hausdorff distance, and what's interesting that we have built complex construction of compact quantum metric spaces. We have built some complex quantum Gromov Hausdorff distance, and these theorems shows converges according to this distance for such spaces, and it's also quantum phase spheres and standard photos and examples of compact quantum metric spaces, and for them the following theorems has been proved. My talk founded on 3 articles. The main articles is Rieffel article, compact quantum metric spaces, Jens and David, they has proved the last 2 theorems in this year, and it's their article, and also I looked in the last article to in the last article, I looked about the space of states. If you have some questions, we can try. We can discuss, and I can repeat some statements. We can try discuss. So that's all.
Okay, thank you, Vladislav, for the very interesting talk. Questions, please, or remarks? Well, let me ask a question. It is related somehow to Podlich spheres. It is known that the quantum sphere is a quotient of a bigger sister algebra, so-called quantum ball algebra, which was studied by Klimek-Lesniewski and later Waxman. So the question is, are there any results, any convergence results about quantum ball algebras? I mean, some known results in the literature about the convergence of such algebras.
In the recent article, I haven't shown. I haven't found.
So they don't consider quantum.
Yes, we don't consider quantum balls.
Okay, thank you. Thank you. More questions, please. Well, if there are no more questions, then we thank the speaker. Thanks, Vladislav. So our next meeting will be probably the last one in this academic year, and the speaker will be OC. And the talk will be something about physical origins of some results related both to physics and to sister algebras.